So in the previous section, we've learned how to do line integrals on the plane. So now we're going to do line integrals in space. Not much of a difference. It's the same concept, except that now our path would be in 3D, would be some motion in 3D space, but we would break it up in the same way and then apply a Riemann integral in the same way. And what you get is a very similar formula of the function against what, again, we're going to call arc length, which is the length of the tangent vector dt. So it's the same formula, just extrapolated to 3D. It just works. And similarly, when I compute integrals of this shape, when I call dx, this integral right here would be the integral above the path c, which we've parameterized in some way, of f of x of t, y of t, z of t, times, and if I'm integrating against dx, I'm only computing what's happening in changes in x, so it would just give me the derivative with respect to x dt. And similarly, if I change this differential would be y prime of t dt, and so on. So just very similar to what we have done in 2 dimensions. So let me show you how it works in 3 dimensions. If I want to compute an integral, a line integral, about a path in a helix. We saw this example when we were talking about vector functions. This helix from 0 to 2 pi, it starts here, and it just goes one full loop around the y-axis. And we want to integrate not just, we first computed the length of that helix, of that segment of a helix, but now there is some other function on top. So now there is some function, there's some other value we are evaluating above that line, and I want to compute that integral by straightening that segment. Now it goes from 0 to 2 pi, so time will go from 0 to 2 pi. That is also, I can represent it sort of as a function of t and compute that area, but if I just straighten that without throwing in a correction factor, some sort of Jacobian, then I'm not going to get the same length, because an arc here, a piece of arc here, doesn't have the same length that the corresponding piece of arc here. So we have to correct using the derivatives, using the tangent vectors, do that correction. It works exactly like in 2 dimensions. You take, this is my parameterization of the helix, so I compute the derivative of the helix, that's minus sine t, cosine t, and the derivative of t is 1. I compute the length of my tangent vector, that is going to be minus sine t squared plus cosine t squared plus 1 squared. Sine squared plus cosine squared is 1, so now the length is the square root of 2. So that means that ds, the arc length parameter, is that length times dt, so it's the square root of 2 dt. So the transformation actually changes by a factor of the square root of 2 in this case. So now I can put everything together and compute my integral. So what is the integral that I want to compute is y times sine z ds, and that will be the integral from 0 to 2 pi in time. The y coordinate is sine of t. The z coordinate is t, so this is sine of t. And then the ds was a square root of 2 times dt. So this is the integral of a square root of 2, the integral from 0 to 2 pi of sine squared t dt, which again Just to remind you that sine square of t is 1 minus the cosine of 2t divided by 2. So you can do that integral yourselves with that change of variables, and it turns out this is, the integral itself is pi, so it's pi times the square root of 2 is the total. And again, it's not just the length of the helix, but sort of like the area under the graph of the function that we've drawn on the helix. Let me just set up one more example. Or are there any questions about this three-dimensional line integral? So let me just set up one more example in this format. So now this is throwing everything together, because this is not just an integral with respect to arc length. We're going to be integrating with respect to x, y, and z. And this path takes two different sections. So this is somewhere in 3D. I'm not going to make it whatever. It goes from some point, and then from some point to some other point. So when you have that, there's sort of two very distinct paths. So we do one path, and we do one path. So the integral over one path is going to be the integral over the first path plus the integral over the second path. For the path from 2, 0, 0 to 3, 4, 5, remember that we had that 1 minus t times p. So this is 1 minus t times p times 2, 0, 0 plus t times 3, 4, 5. That would be the path. This is 2 minus 2t plus 3t, and then those contributions are zeros, and then 4t, 5t. So that is 2 plus t, 4t, 5t. The derivatives of that path will be then 1, 4, and 5. And those tell me that dx, that parameter with respect to x, is just 1 dt, that dy is 4 dt, and dz is 5 dt. So the integral that we want to do is going to be the integral. Well, what is the time bounds are from 0 to 1. It takes you from one point to the other. So I'm going to integrate from 0 to 1. The y coordinate, those are what these give you. So the y coordinate is 4t times dx. dx is just 1 dt, so it's times 1, plus the z coordinate, which is 5t, times dy. dy is 4 dt, so I have to multiply by 4. And x is, the x is 2 plus t, times dz, and dz is 5 dt, so I have to multiply by 5. So this is the same integral, but now parameterized with respect to time, with respect to that. So this is just the part of C1, and then you can parameterize the second part and get the total sum. All right, so next time we'll talk about vector fields.